Let's talk a little bit more about convergence and divergence, and let's talk about comparing what we know is happening between two functions. So if we know a function converges, like we just determined in the last video that the area accumulating in the plane from 1 to positive infinity under the function e to the negative x converges and converges to the value of 1 over e. Well, if we know a function converges, what must be true, absolutely must be true, about any other function that is smaller? And by smaller, I mean any other function that lies in the plane everywhere below the function that you found to be convergent. Let's say we know that over the interval that we're looking at from, we'll just say from a to positive infinity, that we determined that that area under f of x converges. And let's say we have another function, g of x, that everywhere on the interval we're interested in as x tends toward infinity for an upper limit, we know that the function g of x, its outputs, lie in the plane below f of x. That's what I mean by the idea of the function is smaller. Doesn't it have to be true then that over the same interval from a up to positive infinity, g of x, that area, must also converge? And so it turns out that it's really important for us to know a set of functions or several functions where we already know what the behavior is. And if we know that a function diverges, what must be true about any other function that is bigger? And we have any other function in the plane that we know over the same interval all of the outputs are higher in the plane than our divergent function, then isn't it true that any other function that is bigger must also diverge? So we really want to know a set of functions, a group of functions, or some shortcut for us to determine if we could compare this function inside this integral that maybe we don't know how to integrate. If we could compare it with another function that we know how it behaves, that would be something really handy to know. So comparing the rate at which functions grow, comparing where they are in the plane, is a really handy way for us to also determine whether the unbounded area converges or diverges. So all we really want to know is, does the area trapped over the interval have a relatively finite value? Does it converge, or does it continue to grow? That's the area, heading toward infinity, positive or negative. Or another type of divergence is, does that area never really settle down to one value and stay there? So sometimes comparing the rate at which functions grow can be useful in deciding if an integral converges or diverges, especially if we're not able to evaluate the integral that we've been given. So let's talk about the idea of convergence and divergence, and then comparing known functions. So here's the function y equals e to the x. We know a lot about this function. We know what the parent function looks like, and we know that it grows very fast. Bigger and bigger and bigger input values lead us to, quickly very huge output values. As a matter of fact, to put it in perspective, if x is 3 inches and y is about 20 inches, then at 10 inches, the output of e to the x, if we had inputs of 10 inches, the output's 1/3 of a mile. That's a function that grows really, really fast. And here we are, let's look at x at 44 inches. Well, the output, the corresponding output to putting that into the e to the x function is 2 million light years. This function grows extremely fast. At 64 inches, the y value is at the edge of the known universe, 10.5 billion light years. This is a quickly growing function. So what we mean by grows faster is if we know how quickly e to the x grows, and we know that there's some other function out there that grows even faster, then if e to the x diverges, then g of x must diverge also, just by comparing their behavior over the same interval. So it becomes really important for us to have a set of functions where we know how they behave. Here's another function we're really familiar with. It's the inverse function to e to the x. So natural log of x grows, but it grows very, very slowly. Same chalkboard, same measurements, all those kinds of things. So we would have to move 2.6 miles to the right before the line moves a foot above the x-axis. That's how slowly this thing grows. By the time we reach the edge of the universe again, the chalkboard line will only have reached 64 inches because inputs and outputs are reversed, right, in these inverse functions. So the natural log function increases, and it increases everywhere, and this area that's accumulating in the plane here is growing, and that area is continuing to head toward an accumulation of infinity. So again, if we have a function that we know is larger than the natural log of x, since natural log diverges, that function must also diverge. And now e to the x and natural log of x are not the only two functions that we can use for comparisons, but they're ones that I want you to see. Not every function has to blow up as quickly as e to the x to be considered divergent. There's still area accumulating. That's how big infinity is. Natural log of x grows so slowly, but infinity is so big that there's enough space there for that area to continue to grow. And so if we were to integrate that from 1 to positive infinity, natural log of x dx, we would find that that area goes toward infinity. So let's talk about comparing functions and what those results are going to look like. This turns out to be really important for us in our series work, but I'm going to go ahead and introduce it here because we can use it when we start talking about evaluating these improper integrals. So we've talked about faster, we've talked about slower. Obviously we would understand same rate of growth as x tends toward infinity. We don't mean that the outputs of two functions have to be exactly the same for the same rate of growth. They just relatively have the same behavior as far as growth is concerned, where they are in the plane as x tends toward infinity. So let's set this up. Let f of x and g of x be positive for x sufficiently large. So we're above the x-axis and we're near infinity. Well, there's some things that we need to know. First of all, f grows faster than g grows slower, as x tends toward infinity if this limit is a true statement. If f lies everywhere in the plane over the interval that we're talking about, here's the x-axis, we tend toward infinity, here's f of x, and here's g of x. If I put those functions in this ratio with f in the numerator, and I see what is happening to the outputs of this function as x tends toward infinity, I'm going to see that f is larger than g if that limit result is infinity. So if the lower function, g of x, diverges, what has to be true about f of x? Well, f of x is bigger. Has to be bigger. That's what this is telling us. So if f of x is bigger than g of x and g of x diverges, then f of x must also diverge. That's pretty helpful. So it becomes really important that we know whether g of x converges or diverges. So what does it mean if the bottom function converges? If we run this limit and we get this result, This tells us everywhere that's important to us, that f of x is bigger than g of x. So if g of x converges, that's telling us, here's f of x, here's g of x, from a up to as x tends toward positive infinity, and we know g of x is a convergent function, and we know f of x lies in the plane above it. That's not helpful. To tell me that f of x is bigger than a convergent function doesn't necessarily tell me f has to diverge. I can have a convergent function bigger than another convergent function. What I can't have is I can't have a convergent function bigger than a divergent function. That's why this is so helpful to us. If f of x is bigger than a divergent function, it must diverge. But if it's bigger than a convergent function, it can do either. It could converge or it could go ahead and diverge. So that result is not helpful. Now, if we run this limit and we get 0 for an answer, what does that tell us about the relationship between f and g? That absolutely tells us that as x tends toward infinity for large input values, the outputs of f are much lower than the outputs of g. That tells us that f of x is smaller than g of x. So what does this mean if g of x converges? Well, what it means if g of x converges and f of x is smaller, then any function smaller than a convergent function must also converge. So if this is g of x and g of x converges, and we prove using this limit that f of x is smaller, then f of x must also converge. Now, what does it mean if g of x diverges? Well, if g of x diverges and f of x is smaller, f of x could do anything. F of x could go ahead and converge, or it could diverge. We can have a relationship where one divergent function is bigger in the plane than another divergent function, but f of x could go ahead and converge. So this result would not be helpful to us. What the power to this is that we need to know what the function on the bottom is doing. We need to start out with a function g of x, and we need to determine its convergence or divergence. Then it becomes very helpful to plop that into a limit with the function in question, the one they've asked us to determine, is it convergent or divergent, and make a comparison. But now, just as we said here, that's not always going to be helpful. Because if g diverges and f is smaller, then that tells us nothing about f. If g converges and f is bigger, that tells us nothing about f. So this limit is helpful if you get the right result out of those limits. And now we're going to go ahead. I'm about to run out of time, but there's a second thing here that's really helpful for us as well, and that's where they grow at the same rate. So we'll pick up here in the next video.